Dear students, today we'll see the extension of LC tank circuit, and we'll go on to build up an oscillator circuit using BJT. So here we will be studying a LC oscillator circuit, and in which we'll see the first type, which is called as Hartley oscillator. So here is the today's topic. We will see Hartley oscillator circuit, and in this explanation, this circuit will be constructed using bijunction transistor, that is BJT. It also has an option that this circuit you can also construct it by using op amp, but here we are going to use BJT to build an Hartley oscillator. Now, basically we know that oscillator is a circuit which is going to produce a repetitive waveform. And here in this circuit, it will be a closed loop circuit. And in the closed loop circuit, we want one condition to be there, that is the phase shift in the closed loop. The total phase shift in the closed loop should be 360-degree, or that is 0 degree. That means there should be no phase shift for the feedback which you give from output to input, so that it becomes a positive feedback. And positive feedback is the basic need to make an amplifier to work as an oscillator. So here we'll see first the definition, and then we will go to see the circuit diagram. So in a definition, we'll see that Hartley oscillator is a type of LC oscillator, that is inductance and capacitance connected in parallel, that is a tank circuit. So it is LC oscillator that generates undamped sinusoidal oscillations whose tank circuit consists of the tank circuit of L and C, which is going to give you the oscillations, which is the feedback circuit. Tank circuit consists of two inductors and a capacitor. In the tank circuit, the two inductive coils are serially connected together, forming a parallel combination with the capacitor. This is introduction to Hartley oscillator. Once we see the circuit, it will be very clear to you how that Hartley oscillator is going to operate. First, how it is constructed, and then second we'll see how it will get operated. So here you can see the circuit of Hartley oscillator. So here our main active component will be this transistor. So here we have used a transistor. We will name it as Q transistor. Okay, it is an NPN transistor which we have put. Now, to this NPN transistor, we have made a configuration of an amplifier. As we have seen circuits for RC coupled amplifier, same type of combination we have made. So here you can see you have the VCC supply plus VCC is given. Now that VCC supply will make a current to flow through this R1 resistor and R2 resistor. Okay, this current which flows will develop a voltage across R1. So here you will have a voltage across R1, and it will also develop a voltage across R2. Okay, so these voltages will act as biasing voltages. So they will act as biasing voltages. So they are going to bias the transistor so that transistor operates in a proper active mode, so that we can use it as an amplifier with positive feedback to work as an oscillator. Okay, so here this biasing should see that the base emitter junction of the transistor is forward biased. This is forward bias, and the base collector junction of the transistor is reverse bias. Okay, so that it is operating in active region. It is operating in active region. Okay, now here it is important because basically this transistor will be an amplifier, and then we will see that the feedback what we give in this closed loop circuit is a positive feedback. Okay, now in the collector we have connected a RFC, that is radio frequency choke. Okay, now here you will be having a coupling, a capacitor CC, which will couple to the output. So here you can get the output. This will be our output, which will be a repetitive oscillations. Now this, how these oscillations are produced depends upon what feedback you are giving. And here you have your RE and CE circuit, so that the circuit is stabilized. and this is the input blocking capacitor. Okay, and here you see the tank circuit. This is your tank circuit. Okay, now here, once the VCC supply is given, okay, VCC supply is given, the a capacitor is charged. So a capacitor is charged here, and the tank circuit will start operating, and the biasing voltages will be given to the transistor, and transistor will get a input from here. Okay, now this is how it will start. Once the transistor has got an input here, that input will go through this base drive, and then you can see at the collector drive, when the input from the base drive is coming to the collector drive, there will be a phase shift of 180-degree because of the transistor. This transistor will give you an output in phase reversal, so there will be a phase shift of 180-degree. Now that phase shift of 180-degree will be given to the feedback network here. Here you are having this feedback network. This complete tank circuit is your feedback network. This is your feedback network. Now this feedback network has to give a phase shift of another 180-degree, so that this will give another 180-degree. So 180-degree by the transistor, 180-degree by the tank circuit will make it 360 degrees. So here you can see it will be 360-degree phase shift, which is nothing but 0 degree, which is nothing but 0 degree. So it is a positive feedback. It is a positive feedback to the amplifier, and this will make it to work as an oscillator. Okay. Now here in this tank circuit, one specialty is that we are not having a tank circuit which is have inductor and capacitor like this, whereas the inductor is splitted into two. Inductor is splitted, and here splitting inductance will see that whatever feedback voltage you get, okay, that feedback voltage will be developed across your L2, that is your output voltage. Output voltage will be developed across L2. Now that voltage will be given here, which will be your feedback voltage, which will go as the feedback to the input here. Clear? Now this L1 and L2 together will make the inductance. Say for in this tank circuit, if you're having this as L and this as C, now this L in this case of Hartley oscillator will be a combination of L1 and L2, where L1 and L2 are serially connected. So if you are having the output frequency because of the positive feedback, the output will be oscillating, and in that oscillations you will get an oscillating frequency. That frequency will depend on that feedback tank circuit, and we know for LC, that is if you're having L and C tank circuit, for that the frequency of oscillations is equal to 1 by 2 pi root LC. Okay, so frequency oscillation is equal to 1 by 2 pi root LC. Now here in Hartley oscillator we have taken L equivalent, which is equal to L1 plus L2. So the inductors in series will be added. Therefore, the frequency of oscillation for Hartley oscillator can be given as 1 by 2 pi under root L equivalent C. Okay, so in the same formula, you have to put the combination of the splitted L1 and L2 both together, the combined effect of L you have to put. So you have to put what is L equivalent. Okay. Now here basically what we have seen, we had a transistor which will be working as an amplifier. Now there is no special input for the transistor. There will be a feedback, and the feedback will be in phase with the input. And because it is in phase with the input, it is called as a positive feedback. And once a transistor is configured with a positive feedback, it will work as an oscillator. Okay, so this is going to work as an oscillator. Now only the speciality in this is your tank circuit, in which you are having L and C. In that, L is splitted as L1 and L2, and C is a parallel combination with that L1 and L2. Okay, so this type of feedback circuit if you are having, then this type of oscillator will be called as an Hartley oscillator. So it's a specialty of Hartley oscillator that the inductance is splitted into two. Okay, so here 180-degree phase shift will be provided by the transistor, and another 180-degree phase shift will be provided by the feedback circuit, that is the tank circuit. So total phase shift of the loop, this is a closed loop because it is having a feedback, that is output is connected to the input. So the total phase shift of this closed loop will be around 360-degree, and that is our basic requirement for an amplifier to behave as an oscillator. Okay, if you want the transistor to behave as only as an amplifier, then we are going to use negative feedback. In that, the gain might go little less, but it will give stability and it will work as an amplifier. But if you want to make the BJT or the transistor to work as an oscillator, then in a closed loop circuit, we should see that the feedback, the total phase shift is 360 degrees. So that it is positive feedback. And because of positive feedback, the output will oscillate, and the oscillations will be supported by your tank circuit, because in the tank circuit, first the capacitor is going to get charged, then it will discharge, and then the L1 and L2 inductance, that is inductance L, will start storing energy in the form of magnetic field. And once the capacitor is completely discharged, that complete energy in the inductance will start getting collapsing. So again, the capacitor will get charged, but in a reverse polarity. So this process of exchange of energies between inductance and capacitance in the tank circuit will go on taking place. The capacitor will go on charging, discharging, charging, discharging in different polarities, and that will give you the alternating waveform at the output. So that is called as oscillations. Okay, this is what we had already studied in tank circuit. Now that same tank circuit, only that inductance L is splitted into two and kept in the tank circuit, and this type of configuration, this type of LC oscillator is called as a Hartley oscillator. Okay, so this is the complete explanation for this. Now we will see the theory part, how the theory is written for this. So a construction of Hartley oscillator. In the circuit diagram of a Hartley oscillator, the resistors R1, R2 and RE provide necessary bias condition for the circuit and also the stability condition. The our capacitor CE provides AC ground, thereby providing any signal degeneration. This also provides temperature stabilization. The our capacitors CC, CB are employed to block DC and to provide an AC path. The radio frequency choke, that is the RFC choke, which is in the collector region of the transistor, offers very high impedance to high frequency currents, which means it shorts for DC and opens for AC. Hence, it provides DC load for collector and keeps AC current out of the DC supply source. Then if you speak about the tank circuit, then here we can say that the frequency determining network, that is a tank circuit, is one which is going to decide what will be the frequency of the output oscillations, how many number of cycles per second you are going to get. Okay, so the frequency determining network is a parallel resonant circuit, that is L and C, which are in parallel, which consists of inductors L1 and L2 along with a variable capacitor C. The junction of L1 and L2 are earthed, they are ground. The coil L1 has its one end connected to base via CC and the other emitter via CE. So L2 is in the output circuit. Both the coils L1 and L2 are inductively coupled and together form an auto transformer. So this is a speciality of your Hartley oscillator. Then working of Hartley oscillator, when the collector supply is given, a transient current is produced in the oscillator or tank circuit. The oscillator current in the tank circuit produces AC voltage across L1. The auto transformer made by the inductive coupling of L1 and L2 helps in determining the frequency and establishes the feedback, as the common emitter configuration transistor provides 180-degree phase shift. That is 180-degree phase shift is provided by the transistor itself, and another 180-degree phase shift is provided by the transformer, which makes a 360-degree phase shift between the input and output voltages. This makes the feedback positive, which is essential for the condition of oscillations when the loop gain, that is feedback gain into the gain of the amplifier, is greater than 1, oscillations are sustained in the circuit. Then how do you determine the frequency of oscillation? So we know that the frequency of oscillation of a sinusoidal generated by the tank circuit. So if you take a simple tank circuit L and C like this, if you take a simple tank circuit, this will be L, this will be C. If you take a simple tank circuit, then the output of this will be oscillations, and here the oscillation frequency will be given as 1 by 2 pi root LC. This is what we have shown here. This is the formula for the frequency of a tank circuit where L and C are in parallel combination. So L and C are in parallel combination. Same thing is going to be used in Hartley oscillator, only that inductance L will be splitted into two. So here, but in Hartley oscillator, we consider two inductors in the tank circuit. Thus, the equivalent inductance will be given as the sum of the two inductors. So L equivalent, LEQ is equal to L1 plus L2. So these are the individual inductors which are added, and you will get the equivalent inductor. Thus, the oscillating frequency is given as 1 by 2 pi under root L equivalent. So instead of L, we are going to put L equivalent into C. So L equivalent will be nothing but L1 plus L2. So what are the advantages of Hartley oscillator? It provides the sinusoidal oscillations of constant amplitude. The oscillating frequency can be changed by the use of variable capacitor. The circuit is not complex. Practically, a single tapped coil can also be used in place of two inductors in the circuit. Then what are the disadvantages? Disadvantages are: number one, due to the presence of harmonics, sometimes distorted sinusoidal oscillations are generated. Number two, it does not find use in low frequency applications. Then here are the few applications of Hartley oscillator. It is used to produce a sine wave of desired frequency, mostly used as a local oscillator in radio receivers. It is also used as radio frequency oscillator. Thank you, students.